Okay, now wow, let's look at the exam problem. Okay, can you hear me clearly?
Yes, bro.
Okay, all right. So the first problem, apparently no one finished this problem completely. So I think you still have the exam problem, right? So this is the solution. So this is the objective function. So what is the objective function? See that we want to know, right, which mine should be operated each year and how much should they produce. Okay, so we have revenue and expenditure for each year. And what else? The final blend or sales, yeah, for 10 USD per ton each year. But we have conditions for royalty and also maximum capacity of each mine. Yeah, and from this table we have royalty, yeah, for each mine. Also upper limit of ore, the amount of ore of each mine, that, yeah, the ore that we can extract from each mine in a year. And this is a quality of the ore from the mine, okay, from each mine. Okay, so actually, for this variable, because we don't know yet, we have to decide which year should be open, and also, in which mines in each year we should work, right? Because sometimes we keep it open, but we don't work on that mine. It is possible. All right, so we have delta and gamma, okay, which represent true or false. It's a binary variable. Only it can be only 0 or 1, right? For example, delta is the logical variable representing if the mine is work in that year. So we have a matrix of delta IT, okay, and delta IT becomes 1 if my I is work in year T, okay, or it can be 0 if we don't work on that mine in that year, right? And for gamma, we have gamma IT. Gamma IT is 1 if my I is open in year T, okay. Then we have XIT. XIT is not logical variable, it's a real number, okay, but it's metric, of course. IT, yeah, my I and year T, okay, it is output from my I in year T. And we have QT, okay, QT is a quantity of blended or produced in year T. All right, so yeah, of course, we have capacity, right? Maximum capacity of each mine, right? So the output from my I in year T, XIT must be less than the maximum capacity of each mine. So we have XIT subtract by MI delta IT. Okay. And of course, because well, delta IT is it's a logical variable. It can be 0 or 1, right? If we work on that mine, of course, this become 1, right? So the maximum capacity becomes MI in that year T. All right. But if while we don't work on that mine in my I on year T, so delta becomes 0. So this value becomes 0, right? Okay, so this term becomes 0, then XIT must be negative, okay, 0, okay? And it cannot be negative, of course, so XIT must be 0. We force it to be 0 because we don't work on that mine, okay? MI is the maximum yearly output from my eye, so it is this one. Yeah, right. This maximum output. Okay. Also, we have other conditions. For example, well, for each year, right? Summation of all the delta IT must be less than 3. So that means, well, we can close only 1. Okay. And delta IT minus gamma IT must be, yeah, negative or 0. Okay. That means, well, if we close the mine already, we cannot work on that mine anymore, right? And this well, consecutive year where if we, yeah, delta IT plus 1, okay, minus gamma IT plus 1 minus gamma IT must be negative for 0. Okay. Also, we have a condition for the quality of the mine, of the ore we extract. Okay, and this condition represent that one. Okay, so for objective function, we have, yeah, we want to maximize revenue, okay, plus that royalty fee. Yeah. Okay. Okay, so well, it's not that complicated, okay, but you need the logical variable to represent whether the mine is open in that year or the mine is, well, we work on that mine on this year. Okay, so for problem number 2, this one, I think, well, most of you can complete this problem. It's quite simple. Well, we want to minimize x1 square plus x2 square. And we have one constraint, one equality constraint. So clearly, it must be, we can solve it using Lagrange method. Okay, so the problem asks us to set up the Lagrange function and find the minimum point. So, well, for Lagrange function, it's just very simple. Yeah, x1 square plus x2 square and plus lambda. Okay, Lagrange multiplier times with equality constraint. Okay, and well, partial derivative of, yeah, Lagrange function respect to x1 first. Yeah. We obtain this, well, 2x1 plus, yes, 2x1 from this term, right? Derivative, yeah, respect to x1. And this term, we have x1 square here. So actually, we have to time with lambda. So it becomes 2 lambda x1. Okay. become 0. Okay, and the next condition is, well, we take derivative of this Lagrange function respect to x2. So we have 2x2 from this term, okay, and plus, yeah, we have lambda 2 lambda x2 square, right? So it becomes, well, 4 lambda x2, 4 lambda x2 becomes 0, okay? And the last one, derivative of Lagrange respect to lambda is clearly, yeah, it's a equality constraint itself. So this one, okay? So you see that in order to solve this system of equation, it's very simple, because from 2x1 plus 2 lambda x1, well, you, of course, you divided all sides of equation by both sides of equation by 2, right? And then you see that it becomes, well, x1 times with 1 plus lambda. So it's clear that, well, x1 can be 0 or lambda must be -1. Okay, in the first case where lambda x1 is 0, so you solve for x2 from this equation, because x1 from this equation, well, x1 can be 0 or lambda can be, must be -1. Okay, if x1 is 0, then clearly x2 is 1 over, yes, root of 2, and lambda is -1. Okay, and from this one, from the second condition, the second equation, we have, yeah, 2x2 plus 4 lambda x2 here. So you see that we divide out both sides by 2. So this expression becomes x2 plus 2 lambda x2, right? So we can solve for x2. Yeah, x2 must be 0, or, yeah, and if x2 is 0, so you solve for x1 from this equation. Okay, so we got 2 points, right? Which one is the minimum point? So, well, you can, well, very simple one, you can, yeah, substitute x1 x2 here with x1 x2 you obtain, okay, and see the, what's it, which one is well, smaller. So that is the minimum point. Okay, but of course I did not, well, the problem does not ask you to find the local minimum point. So you can answer the point which has the smaller value of objective function, that is. But of course, well, both points can be local minimum, right? So you have to check with Hessian to see the curvature of that point at that point, right? But anyway, well, the minimum point is x1 is 0, x2 is 1 over root 2, okay, and lambda is -1. Okay, any questions? Any question? Sakun, you have any question?
No, John.
Okay, yeah, and what about other? Khan, Asan Khan, you have any question on this problem?
No, sir. All right.
Okay,
So
okay, good. Okay, so well, what about problem 3? For problem 3, yeah, we find local extremites, yeah, extreme point, right, of this following problem. And you see that at the objective function is not linear, right? And we have constraints, 2 constraints. The first one is equality, and the second one is inequality constraint, of course. Then you cannot use Lagrange multiplier. You need KKT, Courage-Kuhn-Tucker. Okay. But the concept is very similar because KKT, of course, the fundamental of the KKT is use the Lagrange multiplier, Lagrange method. So we set up the Lagrange function first, which is a summation of the objective function here, x1 minus 1, square of the x1 minus 1 plus x2 minus 2 here, right? The objective function plus lambda times with equality constraint and plus mu, which is KKT multiplier times with x1 plus x2 minus 2. Okay. So from the condition, the KKT condition consists of the first one. It's a partial derivative of Lagrange function with x1. So you can see that it's 2 times x1 minus 1, right? This term. Okay. And where else we have x1 here? Okay, so it might be, oh sorry, this should be, oh right, it is correct. Yeah, we have minus here, so it is minus lambda here, right? Because it's x1 here. And the next one is, we have x1 here, so it must be mu. Okay, so 2 times with x1 minus 1 subtract with lambda, okay, plus mu must be 0. Okay, we have the first equation. And well, if we take a partial derivative of Lagrange function respect to x2, this term becomes 0. So this term becomes 1, right? 1, this term becomes 0. And we have lambda here, plus lambda, okay? And plus mu, okay? Because x2 here, x2, become 1, so it's mu. So the derivative, the condition becomes 1 plus lambda plus mu becomes 0. Okay, we got 2 equations already now. And what else do we need? The first one, it's a Lagrange multiplier. So lambda is a Lagrange multiplier because we have a equality constraint on x2 minus x1 minus 1. So x2 minus x1 minus 1 must be 0. Okay, and for this term, of course, this is real. Actually, it's a KKT. So it's an inequality constraint. So we need KKT, right? Condition. So mu times with this term, okay, must be 0. Okay. This is how we set up the KKT condition. So any points satisfying this KKT condition can be treated as an extreme point, can be considered as an extreme point. So we solve this equation, okay, and you will get the extreme point. Okay, so you can start from this equation first. See that mu can be 0, or this term can be 0. x1 plus x2 minus 2 can be 0. So it is different case. Okay, so it's a can be 0. So if mu is 0, so this term we obtain 2 times x1 minus 1 minus lambda becomes 0, and 1 minus lambda becomes 0, right? So if 1 minus plus lambda becomes 0, so we know that lambda must be minus 1, right? Lambda minus 1, and mu is 0 because, well, from this equation. Okay, so if mu is 0, right? If mu is 0, so we substitute mu 0 here, so we got 2 times x1 minus 1. Okay, and what is lambda? Lambda is minus 1, so it's become plus 1, right? Plus 1, and this is 0. Okay, so we can solve for x1 from that equation. Okay, so x1 is, well, 0.5, and from that, yeah, condition, we substitute x1 here with 0.5, so x2 must be 1.5. Okay, 1.5, you got the solution. Okay, extreme point for problem 3. Okay, now we move to problem 4. For
Adhan,
yes,
why can't we use direct substitution method for problem 3?
problem 3.
Yes.
What's your question?
Why can't we use direct substitution instead of making it Lagrange and then solving it by KKT?
Well, so if you, yes, you can do it, right? You can use a direct substitution, and you can remove this one, right? The x2 minus x1 minus 1 becomes 0. It's equal 0. This, you can remove this constraint, equality constraint, right?
Mm-hmm.
But anyway, you have this inequality constraint.
Okay.
Yeah, and of course you, well, once you substitute it first, for example, this one x2, right? You write x2 equal 1 plus x1. Okay, you substitute 1 plus x1 here, and then here too. Yeah, x1 plus 1 plus x1 minus 2 must be less than or equal 0. You still have inequality constraint, right? So you have to set up Lagrange multiplier in, no, not Lagrange function, and also the KKT condition anyway.
Got it.
Okay. Well, we move to problem 4. So we want to minimize x2, and we have one inequality constraint. Okay. The problem asks us to find all points satisfying the KKT condition for the problem. Okay, so to solve the problem, of course, we have to set up the KKT condition first. Okay, so for the KKT condition, it's a, yeah, we start from Lagrange function first. Lagrange function, it's a, of course, it's a summation of objective function plus, because this is inequality constraint, so we change it. Yeah, we rearrange this, and then we obtain mu times with, yeah, minus x2 minus, yeah, square of x1 minus 1 plus 3. Okay, and from this Lagrange, we find the partial derivative first respect to x1. So this becomes 0, this becomes 0. So we have only this term times with mu. So it becomes, well, mu, it's constant in that case. So it's mu and minus 2 of x1 minus 1 here, right? Becomes 0. Oh, sorry. Accidentally, I finished the Okay. Slide already. So, okay. Okay, so for the next one, we find the partial derivative of Lagrange function respect to x2. So we have this term, right? Yeah, it becomes 1, and this term we have only this one, so it's minus mu here equals 0. Okay. And the next equations, the expression is what's it? KKT, right? So we need the mu time with this expression becomes 0. Okay, mu, yeah, this term mu time with this one becomes 0. So you see that, well, to find the points, yeah, satisfying this equation system, yeah, mu must be 0 first, yeah. And once mu is 0, you obtain this, yeah, minus x2 minus, yeah, square of x1 minus 1 plus 3 equals 0. And because mu is 1, right? So you obtain minus 2 times with x1 minus 1, right? And you substitute mu here, right, as 1. So you can solve for x1. Okay, so x1 must be 1, right? In order to, yeah, so this term can be 0. So once we know mu and x1, we put them in this equation, so we can solve for x2. So x2 is 3. Okay, so it is done. So any more question? Any questions?
No, sir.
Okay. So, well, it's, yeah, let me show some example. And you see that it's I think it's not too difficult, right? And well, just one moment. So, well, it's important to set up the, yeah, you must be able to set up Lagrange function and also KKT condition. You know that once we set up the KKT conditions, so we use the KKT condition to check whether the point, any point, satisfying the condition for extreme point or not, right? So actually, if that KKT condition is too difficult to solve, of course, you can use any numerical method to find the solution for that one, and you test with the KKT condition again. If any point, well, any points you rest satisfied with the KKT condition, of course, it can be treated as extreme point, right? So the idea of that KKT condition is really, yeah, important, okay, for the fundamental of the optimization. Okay, anything else? Any more question? And the other thing is on the modeling part, of course, it's quite difficult, and of course well, especially in during exam, because you have a limited time, right? But what I want to emphasize you is, well, you have to, what's it, properly set up the decision variable first. And well, you can start from the objective function first, and try to link between the decision variable and the objective function, because objective function is more clear than constraints. What is our objective for a certain problem, and try to write down the objective function, write them as a mathematical expression, right, in order to represent our aim. Okay, and then from that point, once you properly set up the decision variable and objective function, then you can list on the requirement, I mean the constraints. And each constraint will involve, of course, each constraint must be a function of our decision variables, of course. Okay, any problem or any question with the modeling part, or classical optimization techniques?
No, sir.
No? Okay. Okay, good. So, well, now we move to the linear programming. Okay. Well, last time I remember that last time I talked on this linear programming. We discuss about linear programming already. Now you know the structure of the linear programming, right? So our objective function, it's linear function, and also all the constraints, it's linear function too. And of course, the concept we solve the linear programming is totally different from what the method, the approach we use to solve either optimization problem. Because of what? Because, well, if you look at the gradients, well, remain constant all the way, right? So in that case, it's impossible, right, to find the extreme point like in classical optimization. Because it's impossible to find the point which the derivatives become zero, right? So the idea is just, well, we find the gradient, of the, or we find the iso profit lines or iso cost lines, okay? And then, well, of course, for example, once we know the gradient, we move on this direction. Well, we minimize the objective function, well, maximize the objective function, but we move backward along that direction. We minimize our objective function. So what we do, it's just we have to identify the feasible region first. Once we know the feasible region, and then we know the gradient of the objective function, so we can identify the maximum point or minimum point, right? Because we want to move, if we want to maximize it, we want to move along this direction as far as possible. But of course, because the feasible region limit us that the solution must be on the feasible region. So like in this case, the optimum point is here, right? Because this is the farthest we go on the gradient direction, gradient of the objective function. Okay, and if we want to minimize it, we move this way. So we stop somewhere here because, it's the last point. We remain inside the feasible region. And this is the farthest we can move, to the minimum point, right? Okay, so that's the idea. For example, we want to maximize this function, objective function. We have set of constraints. Okay. For graphical technique, we draw the gradient direction of the gradient of the objective function first. 2, 1, right? 2, 1, from 0 to 2, 1, right? And then we draw the feasible region defined by all these constraints. So we have this region. Okay, so for graphical solution technique, we have to graph all constraints and determine the feasible set first, and then graph the gradient of the objective function. And then we move along the gradient. We shift the contour line into the direction of the gradient of the objective function. Okay, until the last feasible point is reached, and that point is the optimum point. Okay. Then once we, for example, if we want to maximize this problem, C is our maximum point. And if you want to know this point, I mean the coordinate of this point, so you need, you have to solve the intersection between this line, constraint 2 and constraint 3. Okay, so constraint 2 and constraint 3. Okay, you change it to equality, right? Equation instead, because we know it's active, so it must be equality. So you solve the problem, okay, for the cross intersection. Okay, you obtain this point. Okay, and if you want to know the objective function, you substitute x1, x2 from x1, x2, you solve the problem. Okay, any questions? You still remember, right? Kadim, do you have any question?
No, Ajahn.
Okay, yeah.
Then we need to draw this graph on GeoGebra, right?
Pardon?
we need to draw this graph, make this graph on GeoGebra.
Yeah, it's well, I want to tell you the what is it, the basic idea first, and of course you can do it for only 2 dimensions, right?
Yeah.
If you have x1, x2 only, yeah, it's possible to draw the graph, right? But in higher dimension, you cannot draw the graph, right?
Mhm. Okay.
Okay, so and also last time I told you about the 4 special cases for linear programming. The first case is the case of a no feasible solution exit, right? Okay, where we draw all the constraint feasible region, and we see that, well, the constraint given does not, well, the constraints, I mean set of constraint given does not form a feasible region at all. For example, this case, well, feasible region defined by one constraint is this area, but other constraints form this area. So you see that it's not totally, we don't have feasible region. Okay, so in this case, no feasible solution. So you see that, yeah, you cannot solve this problem anymore because, well, even the feasible region does not exist. All right, so the next one is unbounded optimal solution. In the case of unbounded optimal solution, you see that the feasible region is not closed, it's open in this direction. So you see that we can move this direction if we want to maximize and our objective function point this way. Well, we can move this way to, well, any point, yeah, as much as we want. Because we are not restricted by the feasible region, because the feasible region is open. Okay, so in this case, of course, we cannot define a certain maximum point. Okay, but for minimum point, of course, well, we can have minimum point. Minimum point is here if the feasible region is here. This quadrant, the first quadrant, yeah, minimum point is here if they point to this direction. Okay. And other thing is dual degeneracy. For dual degeneracy, if at least, yeah, one of its adjacent extreme point has the same value of the objective function. Okay. In dual degeneracy, it's much easier to explain using graph. So for example, we graph this, and this is our feasible region. And our feasible region and the gradient, I mean, our constraint here, normal to the gradient. And you see that, well, this line becomes our isoprofit or our contour line, right? Because it is normal to the gradient. Okay, once this line, well, equals our isoprofit, then you see that we can move to this point, right? But this point, well, all the point on this line have, what's it, equal objective function, because it is isoprofit, from the concept of isoprofit. All the points in the isoprofit line has the same value of objective function. So, well, you see that we have multiple solutions here, right? All have the same value of objective function. Mhm. Now you see that in this case, we have multiple solution, okay? And we call it dual degeneracy. Okay, in this case, the solution is not at the corner, but it's on the side instead. And the next one is primal degeneracy. For primal degeneracy, we have unique solution, of course, at the corner. But the solution defined by more than multiple constraints. For example, in this case, we have only x1, x2, which is 2-dimension, right? So actually, in order to define the point in 2-dimension, we need only 2 conditions, right? But this problem, this point is defined by 3 conditions already, not 2 conditions. Mm-hmm. Okay, so we call it primal degeneracy. Okay. Okay, any questions from this forecast? Sasmita, you have any question?
No.
Okay, so who else? Vishudha มีคำถามไหมครับ
ยังไม่มีอะค่ะอาจารย์
โอเค Okay, so well, the graphical technique, well, it's clear, of course, it's very intuitive technique to solve the problem, but we cannot use in higher dimension, right? So, well, we need algebraic solution technique to solve such a problem. For example, we based on the graphical technique, then we develop the numerical technique to solve the problem. So, well, before we can solve that one, we have to introduce you the standard form of the linear programming. Okay, we have canonical form with non-negative right-hand side. Yeah, some problem, only some problem can be transformed to canonical form, right? So for the canonical form, of course, you rearrange the constraint, inequality constraint. All the constraint must be inequality, and inequality constraint must be written such as, well, the right hand side becomes positive, non-negative, right? Okay, you rearrange it, and on the right hand side becomes non-negative. Okay, and you have objective function and then constraint, or the constraint is in smaller or equal. Okay, and bi must be positive. And of course, from this one, you can write in a metric form. You have the metric A, right? Vector X, and also vector C and vector X, and vector B, right? And all X must be positive. Then we adding slack variables, okay, to the, so we maximize the objective function, and then we have constraint on the, because it is less than or equal, right? So if we add with positive value, this less than or equal becomes equal, all right? So it is we add slack variable and we restrict the value of the slack variable, but must be positive, okay, or 0. Okay, so it must be non-negative, right? So for metric notation, yeah, the objective function becomes zx, right? So c is yeah, the vector, okay, x also vector, but a is matrix, x is vector, okay, and I is identity matrix, and s is vector of slack variables, okay, and we have b is a vector, of course, and b, all the b must be positive, okay. So and x and s must be non-negative, right? So all xi must be non-negative, otherwise, well, we replace xi with new variables, new 2 variables, okay. We introduce 2 positive, new positive, non-negative, sorry, non-negative variables to replace x, okay. For equality constraint, use 2-phase algorithm, okay. So for at this point, you cannot solve equality constraint now. We start from inequality constraint first, and then, well, I will introduce you later about the how to handle equality constraint. Okay, and the next one is all constraint must be in the form, yeah, of aij xi less than or equal bi, okay, where bi is must be non-negative, okay. If you cannot arrange your constraint in this form, well, we use 2-phase algorithm, okay. You cannot use, yeah, single phase algorithm. And then from this one, once you can rearrange your constraint, inequality constraint in this form, so, well, the transform all the inequality constraint to by adding slack variables, okay, yes, okay. So algebraic solution technique, yeah, we call the simple what is it, simplex method, okay. We write down in the table of the vector of our decision variable, and then select variables, and then our a matrix, and then identity matrix corresponding to the select variable, and then, yeah, vector of b, right, the right hand side of the constraint. And, yeah, down here we write down the coefficient, negative of coefficient of objective function, because we use negative here because we target at minimizing. Yeah, we start from maximize, so minimizing it must be negative of coefficient. Okay, and you see that we have m condition depends on a metric, right? And now we have n variables and m slack variables. So you see that totally we have n plus m variables. Okay, in order to solve the system of equation, this equation system, you see that we need the degree of freedom to be 0. Okay, so we have only m condition. So, well, we need only, yeah, we need the variable we have must be m, right? Not n plus m, n plus m. Okay, so we separate our variable to 2 groups. The first group we call it basic variable. Okay, so the number of basic variable must be m. Okay, and the rest are non-basic variables. Okay, so you see we're starting from n plus m variables. Okay, and we separate the variables to two groups. And the basic variables contains m variables, and then non-basic variable contains n variables. Okay, and at the starting point, you can see that, well, we can solve the problem if we set these identity variables, this variable related to identity metric, which is slack variables, because these variable, slack variable, we have m variable, well, which is matched with the condition we have m, right? So at the beginning, we set all the our x variable, yeah, or non-basic variable at the beginning become 0. Okay, so, well, it's better to explain using this example. So we want to maximize, yeah, our objective function is 40x1 plus 50x2 plus 100. So, and we have constraint on to x1 plus x2 less than or equal 12, minus 4x1 plus 5x2 less than or equal 20, x1 plus 3x2 less than or equal 15. x1 is greater than, it's non-negative, x2 is non-negative. Okay, so, well, we put all these things in the table. Yeah, you see that we list x1, x2, right? All the this variable we have, and then select variable s1, s2, s3, because we have 3 inequality constraint. Each slack variables correspond to, well, each constraint. Okay, from this one, you see that we plus s1 become, yeah, equal, right? We plus s2 here, it becomes equal. And then we plus s3 here becomes equal, right? Okay, and this 2, 1, right? And this minus 4, 5, 1, 3. Okay, and on the right hand side, all values are non-negative, so we, yeah, it's 12, 20, 15, right? And for the objective function, we have coefficient of objective function, yeah, 40, 50. So we change it to minimize, and then, well, it is minus 40, minus 50. Okay, minus 100. And this coefficient respect, well, it's a coefficient, minus 40 is a coefficient of x1, right? We put minus 40 here, minus 50 here, because it is a coefficient of x2. Okay, and on the right hand side is 100. Okay. So if we draw the graph, of course, it's possible to draw the graph because we have only 2 variables, x1 and x2. We start from this solution, this point. We start from this point, which is x1 is 0, x2 is 0. Okay, and s1 is 12, 20, and 15. You see that it's clear from yeah, here, because as I mentioned to you that because we have only 3 conditions and we have, well, 5 variables, and those 5 variables can be classified to basic variable and non-basic variable. Because we have 3 conditions, then that means, well, we need 3 variables for basic variables. Okay, and 2 variables must be non-basic variables. Okay, and we treat non-basic variable to be 0 first at the beginning. Okay, that means we set x1 becomes 0, x2 becomes 0. Okay, and you can solve the problem, well, because you know that x1 and x2 become 0. So you see from this one, yeah, look at the expression, because here we have 2x1 plus x2, right? And plus s1 equal 12. Okay, you can follow me, right? And you see that, well, if we set our non-basic variable to be 0, x1 is 0, so this term becomes 0, and x2 becomes 0, so this term becomes 0. So you see that s1 must be 12, right? So here, 1 s1 is 12. Of course, s1 must be 12. Okay, and from the second expression, you see that because we set our non-basic variable to be 0, so x1 is 0, so this term becomes 0. x2 is 0, so this term becomes 0, plus s2 equal 12, so s2 must be 12. Okay, so you see here s2 12. Okay, so from the third line, third expression, x1 is 0, x2 is 0, so both terms are 0, so we plus s3, right? Plus s3 equal 15, so you see that s3 becomes 15. So you see that, well, for anytime we solve the problem, we set non-basic variable to be 0, so we don't have to solve that. And then for basic variable, we was it in the matrix, for all basic variable in each line must be 0. Okay, except the one we are dealing with, we are solving it. Okay, so in this, the first line, you see that only s1 is 1 here, and other basic variables are 0. Okay, the coefficients are 0. Okay, so no, that means, well, no matter s2, the value of s2 and x3 are, they become 0, right? Because the coefficient 0 in that line. Okay, in this line too, you see that, well, only coefficient of s2 is 1 and the rest are 0. So you see, yeah, this one s2 is 20. Okay, and for s3, yeah, the same. Or you can look at the column, yeah, for any column of basic variable, yeah, we have only one, yeah, coefficient of 1 at only one point. Yeah, right. Okay, so this is the beginning, right? We are at the point of x1 is 0, x2 is 0, and s1 is 12, s2 is 20, s3 is 15. Okay.
Sir, excuse me, sir.
Yeah.
Sir,
Yes.
Sir, how these values came? S1, S2, and S3, and the 1 0 0 0 1 0 0 0 1. How these values came?
Yeah. Okay. Because, well, you see that from this expression, we have the first constraint, 2x1 plus x2, right? And we change this less than or equal to equal. So, well, we add s1 here, right? You got the point? No? Yeah. Just one moment. I will write it down.
I think, Ajahn,
Yes.
I think he is asking about the identity matrix, how we come about the 1 0 0 0 1 0 and 0 0
Yeah,
1.
right. I got his point that in that identity matrix, but, well, I will tell you how we derive this. Because while we have two x1 plus x2, right? And we transform this equation, this expression to, from inequality to equality, right? x2 plus s1, right? 2. Okay, because this side, you see that this side is less than this one, right? So if you add any positive non-negative variables, you can transform inequality, less than or equal to equal, right?
Yes, sir. Yes, sir. I got you.
Yeah. So we also have this. No. 20. So this one got equal 20. So x1 plus 3x2 x2, and this one becomes x1 plus 3x. Okay. So you see here, if we write in the table x1, x2, s1, s2, s3, right? In this table, you see that, well, the coefficient of x1 from the first one is 2, right? And 1, right? And s1 is 1 here. And we don't have s2, s3 in the first expression. Okay. Oops. Okay.
Okay, sir. So you are writing the coefficients of these x1, x2, and s2, s1.
Yeah.
Not the values.
The coefficient, not value.
Okay.
Okay. So
Yes, sir.
so you see that, well, when we set the value, okay, of non-basic variable to be 0, this one to be 0 because it's non-basic variable, this one is 0 because it is non-basic variable. Oh, this one must be 12, right? Yeah, it is. So our basic variable is this one. Yeah, basic variable, and basic variable. And you see that, you can look at this expression. Yeah, if x1 is 0, x2 is 0, we don't have to deal with this term anymore because x1 already 0, right? x2 already 0. So s1 is 12, right? You see, this one is 12. Because in this line, we don't have s2 and s3, right? Because the coefficient is 0. Okay, and from this, the second line, the second row, again, this term x1, x2, we set them as 0. So you see that s2 must be 20, right? Yeah, this one, 20. And from the third line, you know, well, x1 is 0, x2 is 0. So s3 becomes 15 directly. Yeah, 15. Okay, so you see that in order to solve this set of equation, for each column of basic variable, you see that it must be only one, yeah, element that must be 1, and the rest must be 0. Okay, yeah, 1, the rest must be 0. 1 must be 0, or you can look at the row. Yeah, on the basic variable, this is 1 and the rest are 0. This 1, the rest are 0. Okay, 1 and the rest are 0. Okay.
Yes, sir.
Okay, we move back to the slide. So you see that, well, if we want to improve our objective function, because we want to minimize minus 14x1, minus 15x2, minus 100, right? Actually, we don't have to deal with any constant like 100, yeah. But you see at the beginning, at the initial point, we have x1, x2 as our non-basic variables, and we set all the non-basic variable to be 0, right? And you see that if we look at the coefficient of the objective function, you see now x1, x2 are 0, but the coefficient of x1 and x2 are both negative. What does it mean? It means that if we allow x2 to increase by 1 from 0 to 1, we can reduce the value of the objective function by 50. Okay, because the coefficient is minus 50, right? You see, minus 50. So if x2 change from 0 to 1, the objective function will be reduced, will be decreased by 50. Okay, but in case of x1, of course, if we allow x1 to change the value from 0 to 1, the objective function can decrease from, by 40. Okay, for both x1 and x2 should be introduced to the set of basic variable then, because we can, we allow them to change the value from 0 to other value. But we can allow only one variables at a time. Okay, now we have basic variable of s1, s2, s3. So because the coefficient here is the most negative one, the coefficient of x2, the coefficient is minus 50. So this is the most negative. Okay, so for this one, so well, we should put x2 in the list, in the set of basic variables. However, we can have only 3 basic variables. Now we have s1, s2, s3 in the basic variable, in the set of basic variables. So if we introduce x2 to be basic variables, we have to get rid of one original variables. Any variables like s1, s2, or s3, we have to remove one, right? So we have to choose which original variables, basic variables, to be removed. So the condition, we look at the smallest positive, b over a, okay, the ratio of ba. We divide b, right, by a. Which a? A of from the column this column, because we want to introduce x2 in the system. So we consider x2, right? A of x2. And we check we evaluate the b over a. Yeah. So b over a of the s1 is 12 over 1, right? 12. So it is 12. And b over a of this s2 is 20 over 5. So it is 4. Okay. And for s3, it is 15 over 3, right? So it's 5. So the smallest positive b over a is this line. So this line corresponds to s2. It tells us to, what is it? To get rid of the s2 from the basic variable.
Sorry, Ajahn.
Pardon?
Sorry, if we have any a to be negative.
We don't do that. If any a is negative, we don't consider that line.
Okay.
Okay, we consider only when the a is positive, right?
Okay.
Okay, so here we will introduce x2 to our basic variable, and then we remove s2. Okay, x2 to go into basic set of basic variable, and s2 to be removed from the set of basic variable. Okay, from this one, we know that once x2 enter the set of basic variables, so the coefficient here must be 1, right? So we divide out this line, this row, by 5. Okay, so once we divide it by 5, so the first element becomes -4 by 5. And this is originally 5, right? We divide out by 5, so it becomes 1, and it's 0. And this element originally was 1, so we divided by 5. Okay, so it becomes 1 over 5. And the last one, originally it was 20, so we divided by 5, so it is 4 now. Okay, so we want this element must be 0, and this element must be 0, right? As I told you previously, that each column of our basic variable, only the corresponding element must be 1, and the rest must be 0. Okay, so to make this element to be 0, we subtract this line by this line. Okay, and in order to make this element to be 0, we times this line by 3 and then subtract this line. Okay, so we subtract this line by this line first, and then we obtain this. And we times this line by 3 and then subtract with this line. Okay, we obtain this line. Okay, we obtain this metric. Do you have any question at this point?
Sorry, Ajahn. I think, is it possible for one to just apply Gaussian elimination method?
Yes, yes. It's Gaussian. Actually, it's a basic of Gaussian. Yeah.
Okay.
Okay. So, well, now at this table, at this condition, you see that now our basic variable is S1, X2, S3, right? Our basic variables. And our non-basic variable are X1 and S2. Okay. And you see that from the column of X1, we don't care about it. And also column of S2, now we don't care about it. Yeah, it can be anything because of what? Because our non-basic variable, we treat them to be zero anyway, right? So this one becomes zero, right? Not the coefficient, I mean the value, right? The term, yeah. The variables term with the coefficient. So at this point, x1 is 0, x2 is 0. What about x2? x2 is 4, okay? And s1, about s1, s1 is 8, and s3 is 3, okay? Any questions? Kadim, you have any questions?
No problem.
Okay, you can follow, right? Okay.
Yes.
Okay, so we use the same trick. We consider the coefficient of objective function. You see that now the coefficient of x1 is minus 80. What does it mean? It means that if we introduce x1 to the set of basic variables, we can improve the objective function, right? We can decrease the value of objective function. In other words, if now x1 is 0, of course, because it is non-basic variable. If we change the value of x1 from 0 to 1, we can decrease value of objective function by 80, right? Because the coefficient is 80. Now x1 is 0, right? Once x1 change from 0 to 1, the value of objective function will be reduced by 80. Is it clear? Okay, so while we consider x1 to be our basic variable in the next step. And again, because the number of the basic variable is limited. So once we introduce x1 to the set, we have to get rid of other original basic variables, okay? So we consider b over a again from this line, from this column. You see, b over a in, yeah, this one is 8 over 14 over 5. And for this second line, we will not do it because a is negative, already negative, it's not positive anymore. So we don't remove x2 from the set of basic variables, okay? And what about s3? S3 is, well, 3 over 17 over 5. You see that it's clear that this one, S3, must be removed from the basic variable. So for the next round, we will introduce x1 as our basic variable, and we remove S3 from our basic variable. Okay? So again, if we, yeah, the next round, this one becomes x, s3 become x1, right? So this element must be 1. So we divided this line by 17/5. Okay. Yeah. So we divide out, yeah, by this one by 17/5, and then we obtain this table. Okay. And we have to make this element to be 0. This element must be 0 too. Okay. So in order to make this one to be 0, we times this line by 14/5, and then we subtract with this line. Okay. For this one, we times it with 4/5, and then we add with this line. Okay. So the Gaussian elimination, of course, yeah, this element becomes 0, this element becomes 0, this 1, and this element, well, of course, we have to make it 0 too, yeah, by times this line by 80, and then we, yeah, sum with this line, yeah. So we obtain this one, this table. Now we have basic variable. Our basic variables are x1, x2, and s1. Okay. And x1 is 94/17. X2 is 18/17. X1 is 15/17. Okay. We use the same trick because, well, we consider the coefficient first, and then we see that S2 is negative. The coefficient of S2 is negative. That means, well, if we change the value of S2 from 0 to 1, we can decrease the value of objective function again. Okay, and we test B over A, yeah, and we found that, yeah, this S2 should be introduced back to the basic variables. Okay, so, well, now we at this point. Once we introduce S2 to the basic variable, the first step, well, we make this element to be 1 by divided all element by 5/17. We obtain this one. And then we get rid of, yeah, we make this element to be 0, 0, 0. Okay. We obtain this table. And look at this table. We look at the coefficient of objective function. We see that all the coefficient of objective function now positive. What does it mean? If, well, of course, S1, S3, it's our non-basic variable. And you see that if we allow S1 to change from 0 to 1, we cannot improve the objective function because the objective function value will be increased instead of decreased. Okay, and S3 too. If we allow S3 to change from 0 to 1, we lost, yeah, the objective function by 13, right? Because the value will be increased instead of, the value of objective function will be increased instead of decreased. Okay, any questions? Asan Khan. You have question?
No, sir.
No, okay. So Ahmad, what about you? Is it clear for you? Ahmad? Ahmad Hassan, Christy. Saku, what about you, Saku?
No, John. No questions.
Okay, no question. All right. So now the feasible region is here, right? So our solution is that this point. Okay. So you see that along the way, by using simplex method, we start from this point, right? 0, 0, yeah, 12, 20, 15. And then along the way, we move, yeah, from one corner to corner, right? To another corner, to the next corner. Yeah. And from this point, we move to this point. And then finally, we move to this point. Okay. And this is the simplex method. Okay. You see how it works. Okay, let us break for, well, 5 minutes. Okay, then we come back again with the next example. All right, so now we move to the next example. We have a maximization, okay? We want to maximize x1 plus 2x2 plus x3. And we have following constraint, yeah. 2x1 plus x2 minus x3, yeah, less than 2 minus 2x1 plus x2 minus 5x3 is greater than or equal minus 6. And we have 4x1 plus x2 plus x3 less than or equal 6. And all xi, that means x1, x2, x3, they are all non-negative. Okay. All right. So no problem on the xi, right? No. All the decision variables are non-negative. And we have to rearrange some, yeah, for this one, for the second constraint. You see that the right hand side is negative. So we have to change this one to positive by, yeah, we multiply this expression by -1. So we obtain 2x1 minus x2 plus 5x3 less than or equal 6. Okay, right? So we transform it to this problem. Okay, and of course we maximize x1 plus 2x2 plus x3. It is equivalent to minimize minus x1 minus 2x2 minus x3. So we add slack variable s1 here, so it's become equal, right? We add s2 here, it become equal. We add s3 here, become equal. Okay, so what we have here, we write down on the coefficient to the table, right? 2, 1, -1. Sorry, 2, 1 minus 1, right? And 1 at S1, okay? 1 at S1. And here 2 minus 1, 5. 2 minus 1, 5, and 1 at S2. And for the last one, 4, 1, 1, 4, 1, 1, and 1 as coefficient of S3 here. All right. And on the right hand side, we have 2, 6, 6. Yeah. 2, 6, 6. Yeah. And the coefficient for the objective function is -1, -2, -1, right? -1, -2, -1. Yeah. Okay. Any questions at this point? Hadim, you have any questions at this point? No?
No problem.
Okay, good. All right, so, well, you see that our basic variable, we have S1, S2, S3, right? As our basic variable. And yeah, not basic variable is X1, X2, X3. And you see that the initial point is at 0, 0, 0, and 2, 6, 6, yeah. 0, 0, 0, 2, 6, 6. Yeah. Then we, what's it? We look at the most negative coefficient of objective function because, well, by adding x2 to the basic variables, we can reduce the value of the objective function, right? Because we want to minimize it. Yeah. It
Sorry,
benefit. Yeah.
So if the coefficients of the objective functions are all positive, do we look for the least positive?
No. No. Because if they are all positive, you stop the algorithm because you change well from 0 to 1, you even the small amount, but it's penetrate the objective function, right? Because we want to minimize it. Mm-hmm.
Okay.
Okay, so, well, then we add what's it? X2 to our basic variable, and then we replace it with S1. No, we replace S1 with X2, okay? In our basic variable, in set of basic variables. Yeah. So now we move to the point 0 to 0, 0, 8, 4. Okay. Well, later, of course, after the class, you can do it by yourself. I mean, well, you open, yeah, you use Excel. Yeah, Excel is good. You use Excel and try to do it by yourself, and then check with what what you can see from this slide. Okay. Okay, so the next step is we introduce x3 to the set of basic variables, yeah, because the coefficient is the only one which has negative coefficient of objective function. So we introduce x3 and we get rid of s2 from the set of basic variable, and then we follow Gaussian elimination, and then, well, we obtain this. Okay, so at this point, we stop on the algorithm because, well, all the coefficient of objective functions are positive already, so that means we cannot improve the objective function anymore. Okay. Yeah, you can repeat by yourself and then check, right? And the next one, the example, we minimize of minus 3x1 minus 2x2. Okay. At this point, you don't have to change from maximize to minimize because it's already minimized. Okay. And for the constraint, of course, you have x1 minus x2 less than or equal 1, which is, yeah, on the right hand side is 1 already. It's good. And this one, 3x1 minus 2x2 less than or equal 6, which is, yeah, positive already. And all x1, x2, yeah, they are both non-negative, which is good. Okay, so while we put everything in the table. We have x1, x2 as non-basic variable. x1, x2 are basic variables, and then the coefficient is 1 minus 1, right? And then 1 for s1. And 3 minus 2, yeah, and 1 in front of the s2, all right? And the right-hand side is 1, 6, 1, 6 here. And objective function is minus 3, minus 2, minus 3, minus 2. Okay, we begin at this point. Yeah. And you see that, well, the algorithm suggests us to add x1, as our basic variables. Okay, so we add this to our basic variables, and then, yeah, it's okay. And then we have to remove one variable from the original basic variable. In this case, we consider b over a, right? B over a here is 1, b over a here it's 2. So this is the smallest positive one. So we remove s1. We introduce x2, x1, and we remove s1. Okay. So for the second step, our table include x1 and s1 as our basic variables. Okay, so we use Gauss elimination to, yeah, make this point at 0. So, well, we move from this point to this point. Ready? Then this is a special case, because you see that, well, once we reach this table, and well, our basic variables are x1, x2, but we cannot further do anything, right? Because of what? Because even the coefficient, we see that from the coefficient of the objective function, we have negative here. So the algorithm suggests us to include s1 as our basic variables, but we cannot do that because you see that if we consider b over a, right? B over a, but the coefficient in front of s1, they are all negative, right? All coefficients here in this column are negative. So we cannot further improve that because we cannot, well, remove, yeah, any original basic variable. So in this case, it suggests us that, yeah, we cannot further do it because this case is unbounded optimal solution. We have optimal solution already, but, well, it's unbounded optimal solution. Remember, at the beginning, I told you the 4 cases, 4 special cases, and this is the unbounded optimal solution. Okay. Okay. So I suggest you to repeat this problem again. Okay, by yourself, and then see. So we stop at this point because we cannot do anything, right? Any questions for this example? No? Okay, so well, we stop at this point. Yeah. 4300. Yeah, 4300. And you see that the feasible region is unbounded. So the next one is a two-phase of the simplex method. So previously, you learned about the simplex methods, but well, it's limited by what's it? The simplex method we previously deal with, we cannot deal with the equality constraint, right? Because we have to start from inequality constraint and then we add some slack variable to change it to equality constraint, right? To equation. Yeah. But originally, if the problem is equality constraint, we cannot do that. Okay. And the next thing is on the right hand side, the B value must be positive. No, not positive, non-negative. Must be non-negative. If you arrange your constraint and you end up with expression containing the negative left hand side, you have problem. You cannot do that anymore. Okay. So we have to use two-phase algorithm, two-phase of the simplex method. Yeah. So the idea of the two-phase algorithm, if you have equality constraint at the beginning, you add it with E1. You add extra variables, okay, E1, right? For any equality constraint, you add one equality, one variable. Add one variable. For example, we have x1 plus x2 plus x3 equal to, we transform this equation to x1 plus x2 plus x3 plus e1 equal to, okay? Okay, and if we have this kind of thing, you see that it's x1 plus x2 plus x3 greater than or equal to. You see that right hand side is positive, it's non-negative, but the relationship here is greater or equal, not lesser or equal. So in this case, well, we have to arrange the right hand side to be positive, but we don't, but we leave this relationship here as greater or equal. And then we add artificial variable, one artificial variable, for example, E1, and we subtract it out by S1, okay, which is our slack variables, okay? So for this type of inequality constraint, you need two extra variables. The first one is slack variable, and the next one, the other one is artificial variable, E1, okay? So phase one of the method, we define a quantity of W, which is the sum of artificial variables. W is E1 plus E2 plus any extra artificial variables to W. And then the expression of W in terms of artificial variable, like Y1, Y2, is known as infeasibility form. Okay, so for phase one, if W is greater than 0, no feasible solution exists. Okay, so we have to minimize the W to be 0 first. And then the resulting problem will be solved by simplex method again in the phase 2. That's the reason we call two-phase of simplex method. Okay, now look at the example. You will understand from the example. For example, we have this problem. We want to minimize 2x1 plus 3x2 plus 2x3 minus x4 plus x5. And we have two equality constraints. The first equality constraint is 3x1 minus 3x2 plus 4x3 plus 2x4 minus x5 equals 0. And the other one is x1 plus x2 plus x3 plus 3x4 plus x5 equal to. Okay, all Lisian variables x1 to x5 are non-negative, which is good. But we have equality constraint here. So we have to transform this one to this one. Okay, by adding E1 here, adding E2 here, the second, so first and second constraints respectively. And we sum up on the this objective function. We write the objective function as a function of the we write here because our objective function is, let's say, f is a 2x1 plus 3x2 plus 2x3 minus x4 plus x5, right? So because f equal this term, right? So we change to the same side. So this term minus f must be 0, right? Okay, and we define the w here. W is summation of E1 and E2, summation of E1 and E2. That means E1 plus E2 minus W becomes 0. Okay, any questions at this point? Asan Khan? Asan? Kadim?
No, Ajahn, I'm okay.
Okay, I'm happy that you say you're okay. All right. Okay, so the next one is we have to get rid of the E1, E2 from this expression, this equation. So by replacing, you see that we know that, well, if we sum this line with this line, we obtain E1, E2, right? So we replace that one, we sum up that one with this one. No, we sum this one and this line and this line, and we subtract with this line, okay? Because this line has E1 plus E2, right? So you got this one, okay? Not sure or you can start from this one. It's easier. Start from this one. E1 plus E2 minus W becomes 0, right? You subtract with this one and this one, this line. Then you can get rid of E1, E2 from the equation. So finally, you obtain this line. Minus 4x1 plus 2x2 minus 5x3 minus 5x4 minus W. And the right hand side become minus 2. Okay, because here we start from here, right? From this equation. This equation subtract with this one and with this one. All right. The last equation, we subtract the last equation with the first equation and the second equation, and we obtain this equation. Is it good for you?
Yes, John, got it.
Okay. And then, well, we write all these in the table. Okay. So at the phase 1, as I mentioned to you, we have two phases now. The first phase, the target of the first phase is not to minimize the objective function, but minimize W instead.
Sorry, Ajahn. From the previous slide,
Yeah.
you said to get rid of E1 and E2, we add the we subtract the third equation from the first and the second?
Yeah, right. Yeah. Yeah. You start from this one, right? This last equation, and then you subtract the last equation with the first equation and the second equation. And you obtain this one. Okay?
I'm thinking we may still end up having E1 or E2 because no.
No, because you have E1 here, E2 here, right? Once
Okay,
you start from this one, you subtract with this one, E1 will be cancelled out, and E2 will be cancelled out, right?
Yes, I understand.
Okay, so from this one, yeah, as I mentioned to you, the target of the first phase is not to minimize the objective function, but minimize the W. W is summation of E1, E2. Right, because E1, you see that at the beginning, well, we add E1, E2 here, right? E1, E2 here. In order to satisfy the constraint, the summation of E1, E2 must be 0. Okay, so we try to minimize it first. And while you write down the coefficient of the first equation here at first line. Okay, and coefficient of the second equation here, the second line. Okay, and for objective function, well, it's clear. Yeah, the objective here. Okay, and for the last line, yeah, -4 to -5, -5, yeah, -4 to -5, -5, 0, 0, 0, and -2 here. Okay, so from this slide, you, yeah, transform it to table. Okay, it's okay. And then from this one, of course, in order to minimize W, yeah, we can select this column or this column, right? But we select this column. Okay, and it's okay. You can try select this column and do it by yourself. But in this example, I use this column. Yeah, I I add x4 as our basic variable, and then I remove E1 from, yeah.
On what basis we select the column?
Yeah, the
Why
negative.
don't we go for
Pardon?
Why don't we go for x1 or x2 column?
Well, the most negative, most negative. You see, the most negative is -5, right? Okay.
Okay.
Yeah, but for x3, x4, they are both -5, so you can select x3 or x4 if you want, right? But I want x4. Yeah. So, wow, which one to remove? So you consider B over A again, yeah. And then, well, you select this one. That means, well, we introduce x4 as our basic variable, and we remove E1 out. Okay. And then this column, you see that we use the same trick. We use Gauss elimination to make this 1, 0, 0, 0. Okay. And we end up with this table. And from this table, of course, you find the most negative one, and x2 has the most negative coefficient, right? So we add x2 as our basic variable, and we have to remove 1. And of course, because x4, the coefficient in the x4 column, it's x4 row, it's already negative, so you have no choice. You have to remove E2 from basic variables. So at this step, we introduce x2 as our basic variable, and we remove E2. Okay. Okay, so we end up with this one, 0, 1, 0, 0. Okay, this column. And you see that from this table, yeah, finally, the the right hand side of W is 0. That means, well, the summation of E1 and E2 becomes 0 now. That means, well, we can continue with phase 1. We can remove this out. Yeah, we can remove, no, just the one line down here. Okay, so we reduce the table. Okay, we can remove E1, E2 too, and this one, because E1, E2 already, yeah, we already remove it from the basic variable, yeah, and the summation of them is 0. Yeah, we remove this, and remove this. Okay, so we have this table, and at this table you see that we have negative coefficient here, x5. That means, well, if we introduce x5, we can improve our objective function, because this is phase 2 already. So that means, well, we focus on minimization of the objective function, not minimization of W anymore, right? So this is the only negative coefficient. So we introduce x5, and then we consider B over A, and yeah, we remove x2 from the basic variable. So the next round we have x4, x5 as our objective function, basic variables, and the rest are non-basic variables. Okay, and we end up with this table. And this table, you see that we don't have any negative coefficient. So we can stop our algorithm and we obtain the solution. Okay, you can repeat it by yourself. Also, the next, the next problem, we have maximize of, minus 2x1 minus x2 plus 5x3, and we have constraint, and this constraint too. And you see that this constraint, it's a right hand side is negative, right? So you have to divide it. No, divide is okay, but multiply is better. Multiply by minus 1, and then you obtain minus 3x1 minus plus 2x2 lesser than or equal 18, right? Which is, it's okay, But the second one, the third one, you see that we have 2x1 plus x2 minus 2x3 lesser than or equal minus 4. So we have to multiply by minus 1. So it becomes minus 2x1 minus x2 plus 2x3 greater than or equal 4. Okay, like this. So we change the first line to be minimized, and we change the constraint where in order to make the right hand side to be non-negative, right? And then from this one, this is lesser than or equal, so you add slack variable just plus s1. Here also you add just plus s2, but here it's positive, it's greater than or equal, right? So you have to subtract by slack variables and plus e1. Okay, this is a condition, in artificial variable, which is a condition for two-phase algorithm. So we write down again, our W is only E1 because we have only one artificial variables. W is E1. So we see that we change E1 minus W becomes 0, right? So we subtract this line, this E1 minus W equals 0 by this, the third condition, Okay, so by subtract this one with this one, we obtain this one. Finally, we got 2x1 plus x2 minus x3 plus s3 minus w equal minus 4. Okay, so we put all these coefficients in the table again. Okay, so this is the the first one, the second one, the third one, and this objective function and our artificial variables. Okay, yeah, 2, 1 minus 2. Yeah, you see, we got this one. And again, for the first phase, we focus on W, not F. All right, we minimize W, not objective function. So you see, look at the coefficient. You see, we see the column of x3, right? So x3 must be basic variables. And the basic variable at the beginning is S1, S2, E1, not S3, because S3 cannot be the basic variable at the beginning because the coefficient is -1. It's not 1, right? The one has a coefficient of 1 is E1. So basic variable is S1, S2, E1. All right. And then we introduce X3 to be our basic variable because of this negative coefficient here, -2 here. All right. And then we remove E1 because the smallest positive B over A. Right? Okay. So we obtain this table. And from this table, you see that W already 0. So we can remove this row, this line, this row. Okay. Also E1, because E1 is not in the set of our basic variable anymore. So we remove this column and we remove this column, and then we can use two phase, the phase 2 of the algorithm with this one. Okay. And then we introduce x1 as our basic variable and we remove s1. Okay, because yes, this is the most negative one and the smallest positive B over A. Okay, and we obtain this table. And from this table, you see that we have two columns, this column and this column, which has negative coefficient, but we don't select this one, even it is the most negative one because all the coefficients are negative. So we select this column instead. Okay, we introduce S3 instead because, well, we have some of the coefficients positive, right? Okay, so finally we end up with this one, and then, well, we still have non-negative negative coefficient, right? So we introduce x2, we remove s2 here, so we end up with this one. Yeah, and finally we end up with this one where the coefficient of objective function is still negative, but we cannot remove any previous basic variables out of the set because all the coefficients here are negative. Okay, so that means, well, we have unbounded optimal solution here. Okay, when we end up with this similar situation. Okay, any questions? You read it again and you repeat everything by yourself, and then, well, you can also try this example, okay, by yourself, and then, well, next week we will deal with duality, and new algorithm to deal with linear programming. Okay, so any questions? We finished today class. Asan Khan, you have any questions? No, Asan Khan is not here. How about you, Ahmad? Kadim?
No, I'm okay, Ajahn. I'm good.
Okay. Sasmita, are you okay?
Yes, I will try it again.
Okay, you read it again and repeat
Yes, bro.
our example, and then, well, you
Yes.
you will understand.
Yes.
Yeah, and Vichuda.
ยากมากเลยค่ะอาจารย์แต่ว่าเดี๋ยวจะกลับไปทวนอีกค่ะ
Cap, okay. And what about you, Saku?
No, sir, I'm good.
Okay, good. So, well, we finished today class, and then, well, when I get the recorded video, I will put the video and send you the link. Okay. Okay. So, have a good day, everyone. Bye bye.
Bye bye.